There you go. I will begin with a word of prayer. Heavenly Father, we thank you for this day. Thank you for the students. Just ask that you bless our work today, Lord. In your name I pray. Amen. Okay, so I should remind you, we ultimately came to the following definition. We said that two functions, f and g, on a set E, which is measurable, a measurable set, all right? Are equal almost everywhere if f of x is equal to g of x, or if f of x is equal to g of x for all x in E minus S, where the measure of S is equal to what? 0, right? In other words, two functions are equal if they agree everywhere except for possibly a set of measures 0, right? And of course, that set S could be the empty set, and then we just have plain old garden variety equality, right? So two functions which are equal on E are also equal almost everywhere. Okay. And so up to this point, he's listed 5 properties of measurable functions, right? So let me just reiterate those properties just to get us, get going on what we're doing today. So property 1, what was it? Property 1 it said that the inverse image of open and closed sets is measurable, are measurable. Right? Well, let me, I don't want to write these all out again. Let me stop writing these because otherwise it's going to let me use words. So property 1 says that a finite valued function f is measurable if and only if the inverse image of every open set is measurable. Page 28. Thank you. Good question. Page 28. And if and only if the inverse image of every closed set is measurable. So for a finite valued measurable function, we have that the inverse image of open and closed sets are measurable. Property 2 speaks to the composition of a measurable function with a continuous function. If f is measurable and finite valued, then phi composed with f is measurable. Property 3 is about sequences of measurable functions. It says that the supremum, the infimum, the lim sup, and the lim inf of these sequences of measurable functions is again measurable. And I guess I probably should define what measurable function means again, right? Because I think that might have dimmed in our memory a little bit, right? What does it mean for a function to be measurable? Well, what's it mean for a set to be measurable? probably should reiterate those too. What E is subset of D is measurable. What's that mean? Right? There exists open set such that what? Oh. Right. And in that case, we say that the measure, well, okay, right. And how do we define exterior measure? By looking at unions or intersections of cubes is appropriate, right? Okay, so that was measurable set, and then, of course, I should remind us that a function, f, defined on a subset, a measurable subset of Rd, and I suppose at the moment we're looking at real valued functions, aren't we? That is measurable if what? For all A in the reals, the set F inverse of the closed interval from minus infinity to A not included is measurable. We had a notation for that. This was equal to, what was it? F less than A, right? All right. So we have those properties, property 1, property 2, property 3. Property 4 says that if we have, I'll write down property 4 since I can write it down, and I think it's interesting. Okay, fine, they're all interesting, but this one's more interesting. Property 4. Sequence a collection of measurable functions, Fn, n equals 1 to infinity, collection of measurable functions. All right. And suppose that they pointwise converge to F. All right. Then F is measurable. Now, to be I mean, this statement here is, I think, intentionally vague in here. Which x does this hold for? So he wants these to be a collection of measurable sets on E. And initially, this is supposed to be for all x in E. All right? I believe that's how the property 4 is supposed to initially be read. Okay? And then property 5 is what we ended with last time, more or less. F and G measurable, F to the K, F plus G, and FG measurable. All right. Given, of course, that F and G are measurable, and also in the part 2, we need that both F and G are finite valued. All right. Okay. But then he follows up here after he defines almost everywhere. He's like, but by the way, all the properties of measurable functions, I've stated them as if they have to hold for all x, but all of these statements can be weakened. In fact, property 4, you could cross out. You could cross this out, and you could say almost everywhere. So if the limit of fn of x is equal to f of x almost everywhere, it follows that f is measurable. And so anyway, that was that. And that leads us to the statement of Littlewood's three principles, which I probably should state here since we were done with that. Here goes. So number one, every set, I'm gonna take his three principles and write them in a slightly more correct way. Every measurable set is nearly a finite union of intervals. Two, every function sorry, I'm trying to correct these. Every measurable function is nearly continuous. Now, at least in the statement of Littlewood's three principles in volume 3 of the Prince's Lectures Analysis, he does not have the measurable in the principle. Because, if you're going to sell something, it's always best to overstate your claim a little bit, right? Every basic marketing, right? Bait and switch. Every convergent, is that a topic in your other course? Marketing? I feel like marketing is something that we should talk about the ethics of more. Every convergent sequence is nearly uniformly convergent. And I've forgotten to be a truth teller here, right? Every convergent sequence of, to be more, truthful. I really mean what? Convergent sequence of measurable functions, right? I think that's what we're talking about here. Every convergent sequence of measurable functions is nearly uniformly convergent. So, statement number one, what on earth does that mean? Every set is nearly a finite union of intervals. What does that mean? Okay, so if I take, let's be more specific. Suppose I take this set, and I mean for it to be in the plane, R2. How is that set nearly, what's that? Oh, we're in R? Do we have to be in R? I think this is in RD. Oh, intervals. Oh, curses, you're right. Gah, fine. You got me. So, I understand now. So that actually his comments about how to interpret the principles in terms of theorems in this chapter are even more important because those theorems give us the generalization of the principle to RD, not just R. that's another importance to the comments which follow this. But yeah, so if we're, fine, interval. So suppose I have this. How do I guess that's the point, is I can almost, right, like, I mean, that's it, right? That red set, almost gets you the whole, and to make it more interesting, we could throw in right, and then you need another one over here. Measurable set, huh? I guess if there's any kind of monkey business, so to speak, it's got to happen on like a set of measure 0 too, right? Like the nasty stuff in sets, the things that are not just involving just intervals or unions of intervals, that involve infinitely many, those always come down to some sort of set of measure 0 kind of thing, I think. You know what I mean? Like if your set is something unpleasant like this, And here, I'll union it with 1 to infinity to make it more fun. So I've drawn the purple part. I should have made this red. Right? If that's my set, it's measurable. I mean, it has infinite measure, right? Because of that ray to infinity. But you could take the open interval from 1 to infinity, right? E is almost just 1 to infinity. I mean, E is equal to S union 1 to infinity, where the measure of S is 0, right? I mean, it's nearly a finite union of intervals. Now, he doesn't come out and say that this is the notion of nearly. He says that the notion of nearly a finite union of intervals was captured by that symmetric difference thing we looked at last time. Part 4 of the theorem, I think I drew the picture of, and we spent a long time. He says that is what this means formally. And then 2 and 3 are theorems that we haven't yet stated that I'll state now. So theorem 4.4 is the careful version of Littlewood's. This is called Egorov. How do you guys want to say that? You guys aren't going to help me out, I suppose. Egorov, okay, yeah. Suppose we got a sequence of measurable functions. Defined on measurable set with the measure of E less than infinity, and suppose that Fk limits to F on E, given epsilon greater than 0, you can find a closed set A epsilon contained in E such that the measure of E complemented by A epsilon is less than or equal to epsilon, and Fk goes to F on A epsilon. He says that this is the third principle, actually. It's like Littlewood's third principle. Every convergent sequence is nearly uniformly convergent. I think that's... I think he's arguing that theorem 4.4 gives us uniform convergence. Well, nearly uniform convergence. He's saying this is what is meant by nearly uniform convergence, I think, is what he's saying. Think about it for a second. What does that mean? What is E minus A epsilon? Yeah, so E, I mean, I don't know what E looks like, whatever, right? And I mean, E could have, you know, it could be fuzzy, I suppose, but A epsilon's closed, so maybe I'll draw it this way just to be boring. What's E minus A epsilon? So that's on the edge, right? What's the importance of closed here? What does it have to do with uniform convergence? What does uniform convergence mean? Do you guys remember? Mm-hmm. 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 Yeah, for little n bigger than or equal to capital N. Yeah. Oh, I always write that second. I don't know why I do. I know what you're saying, but for some reason I write the, I don't know. I write the for all x over here for some reason. You know? Whatever we're looking at. Whatever the set is in consideration, you know, so let's say it's U. This would be uniform convergence of the sequence on U. What does this closed set have to do with uniform convergence? Why is the fact that it's a closed set helpful? Well, I'm going to leave those questions hanging there. Theorem 4.5 is the other one. And this is by Lusin. Lusin. It's probably not how to say that. Probably not how it's pronounced. He says this attests to the validity of the second of Littlewood's principle. So suppose f is measurable and finite valued on E, and E is a finite measure. F measurable on measurable E with the measure of E being finite, all right, then for every epsilon greater than 0, there exists a closed set. He calls it F sub epsilon with F epsilon contained in E and the measure of E complemented by F epsilon less than or equal to epsilon. And such that F restricted to F sub epsilon is continuous. Supposedly this attests to the validity of the second of Littlewood's principles. Every measurable function is nearly continuous. Well, that I can understand. Yep. Uh-huh. Any continuous function on a closed and bounded set must be, how's that go? So you guys are thinking about if we have continuous on a closed and bounded set, then that means that the function is bounded. This is the extreme value theorem. Oh. Sequence of functions. What does uniform continuity of a function mean? Oh, that's right. Delta. I now remember. Thank you. So it's for every epsilon greater than a 0, there exists a delta independent of the point that you picked. Yeah. Sorry, I need to teach real analysis. Maybe I shouldn't teach real analysis. I don't know. Anyway, closed bounded set must be. You said uniformly continuous, huh? And so, what does that give us? Oh, so we had F on a closed set. Every convergent sequence of measurable functions is nearly uniformly convergent. Oh, but I'm still interested in uniform convergence of the sequence. You're talking about uniform continuity of the limit function, I think. Uh-huh. Uh-huh. Take the, uh-huh. Uh-huh. Okay, so you can see a way to see that theorem 4. You think you see a way to see theorem 4.4 as giving us the uniform convergence of a sequence of measurable functions. Yeah. All right. Okay, I mean, this is part of why I wanted to run this course, is just to like talk these things out. And that's, we're closer to it, but maybe we don't completely own these ideas yet. That's okay. Because what we're about to talk about is the main event. So let's see here. I should probably should erase these, actually. So that brings us to the next chapter, which is on the Lebesgue integral. And so the way this chapter works is the integral is introduced in the most simplistic context, and then he, kind of builds it up on more and more sophisticated contexts. All right. So I think the healthy thing to do for us is to just follow along and first try to understand what he means by simple functions. So the 4 steps are simple functions, then bounded functions supported on a set of finite measure, and non-negative functions, and then finally integrable functions, which is the full-blown, Lebesgue definition, which we'll get to not today, probably. All right, I want to work our way to it. But stage 1 is simple functions. So what is a simple function? You guys remember? A finite linear combination of characteristic functions, I think is right. So here we have k equals 1 to n of a sub k, that's a constant, and chi e sub k of x. Now remember here, chi e k of x is equal to what? It's equal to 1 if x is in ek, and it's equal to 0 if x is not in ek. So this is the set theoretic analog of my beloved Kronecker delta. All right. So in your other book, Emily, right? That's the notation we were looking at earlier today. But anyway, now more than this though, this is not. There's more fine print. There's more fine print where E1, E2, En are what? Measurable, right? Finitely measurable, right? So the measure of each one of those is less than infinity. And so he says the trouble with this, logically, is that you can write a given function more than one way, right? He gives the example of just taking 0 and rewriting it as chi e minus chi e, And so that's symptomatic of the problem. He introduces what's called the canonical form here. So his canonical form is to attain a unique decomposition into simple function. Unique decomposition is simple function. And what he does is he says, it's the unique decomposition as above, except a little bit of fine print, where the numbers a sub k are distinct and non-zero, and the sets e sub k are disjoint. Assume that a sub k is not equal to 0 for all k, and also ei intersect ej is empty for I not equal to j. So if you make those additional assumptions on your simple function, okay, it's okay. Then he's saying that decomposition up there is unique. All right. But okay, so suppose you have a simple function. How do you find the decomposition? So why would it, why wouldn't that already be the decomposition? I mean, why wouldn't that already be the canonical decomposition? Because we don't make part of the definition of simple function what? That the sets have to be disjoint, or that the numbers have to be non-zero. All right? So just because it's a simple function doesn't mean that it's already in canonical form. How do you construct the canonical form? What's an algorithm? He says it's pretty simple. Here's what he says. So since this is finite, let, C1, C2, Cm be non-zero, So select the non-zero. It's a finite list. You can select the non-zero ones. Right? That's step one. And then he says set f sub k equal to x such that phi of x is equal to what? ck. Oh, I wasn't greedy enough. It's not just that they're non-zero. They're non-zero what? What's that? Oh, no, nothing so complicated as linear combination. No, you're working too hard. I want them to be distinct and non-zero. Distinct. Certainly you can do that, right? If A1 is 3 and A2 is 3, just keep one of them in your list, Then what? All right, well, he says then the sets f sub k are disjoint. Do you believe that? I think that's kind of immediate from the definition, right? And he claims that then phi of x can be written as the sum, I'll say I, equals 1 to big M of, well, C sub I, chi, of f sub I, of x. I mean, that's a claim. Can you see that those are equal? I mean, this function. What is the domain of phi? I guess that's the thing I'm missing from the start of all this. What's the domain of the simple function that we're talking about? It's not really stated, is it? But it seems to me like it should be some set which contains. I mean, my picture of it mentally is something like this. This is E. And then these are the E's, So if I say that this is for all x and E, where E contains the union over K of EK is contained in E, certainly, right? And then if I think about, first of all, if I think about phi of, if x is not an element of the union over K of EK, then what happens? Well, that means that x is not in any of the EKs, which means that all of the characteristic functions are 0, so phi of x is 0. But you can also see that, let me call this phi tilde for this moment. But that's also equal to phi tilde of 0, right? Because I mean, this, to be more, I mean, he didn't state the universe. He didn't say where x is from, right? X is from E, yeah? I think, what's that? Yeah, right. Well, I think that's, well, I think, mm-hmm. Well, in that case, the canonical construction is just 0. No. Oh, you're saying, how does this construction go against his chi-e, this thing, right? It does seem like that would have C1 as, C1 would be 1 and C2 would be minus 1. Oh, but then the F is empty? Oh, so we're okay then. I mean, the full set, I mean, there's a missing sentence on the board, set fk this, and if for fk non-empty, keep that k. If fk is empty, delete it from the list. I agree. Thank you. I mean, that yes. I mean, that's what we have to say. Otherwise, as you point out, if we keep ones where the f is empty, then it's not a good, it doesn't, no, I mean, it might still actually, yeah, it's not a canonical form. I mean, if you, what's the characteristic function of the empty set? See, I was thinking it's the 0 function, but I don't know. Man, I'm glad Sam's not here right now. All right. 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 But the larger point here is that if you think about x, it's either outside the scope of all of the e sub k with non-zero values, right? Or it's in one of the EKs, but that's a place where there's a 0 value for the coefficient, which means it's still 0, right? So if it happens to be in an EK which has a 0 coefficient, right? Then this is automatically 0 because it's not covered by that one. So it becomes 0 because this doesn't have a non-zero characteristic function hitting that value. It becomes 0 for a different reason. Instead of it being 0 because the coefficient is 0, it becomes 0 because it's not covered by any of the f's. So it's converting, this canonical form thing is converting 0 coefficients to 0 sets in some sense. Uh-huh. Interval from 1 to 2? Oh, I don't know what you're saying. I'm sorry.
I was trying to construct so that I can refute the.
So you can what?
So that I can refute that.
Oh, you're trying to refute my argument. Oh no. Phooey. So what? Fine.
Because there might be, I mean, there can be overlapping decays to each other, and when you put x into that overlapping, the result is going to be the sum of the coefficient, which is not included in any of your.
Oh, so you're thinking about what if we have chi-e of x plus chi-e of x, something like that. Then what does that do? It doesn't seem like we've accounted for that in the construction, is your point. Because it would say C1 is 1, and it does seem like, oh, wait a minute. Here's the rub. So F, all right. Well, no. Excuse me. C1 is not 1. The only values which, yeah, C1s have to be 1.
But there is no different C2 now, right?
Right, there's just C1. But F1 is empty. That's what I'm about to say.
Yeah. Then your new function is 0.
Yeah. What the what? Hey. Am I missing something? Am I misreading it? Have I misinterpreted his? All right, so I think there is yet another step before the algorithm begins, which is to not do this.
Well, yeah, does that fit in the original definition anyway? It doesn't look like you can have E repeat.
No, I think you can. I mean, the simple function, there's no assumption that the E sub 1s, E sub 2s are distinct, or as far as I remember, there's no assumption that the measurable sets of which we're building are distinct. But to avoid this problem, we should just collect. It's a finite linear combination, right? So it's unambiguous to collect these. To avoid your counterexample, I make it 2 chi-e, and then my C1 is 2, and everything's fine and dandy. I mean, the simple function is built from summing together finitely many of these characteristic functions with constant coefficients. So. Yeah, I think first we take this, right? And if there are any of these which are the same, we add those together. And then we take those and we do this. Yes, so there's a little bit of something missing in this paragraph, right? I mean, fine. Thank you, guys. It's good, but let's go on. Anyway, do you agree that up to some like annoying, picky stuff, we can definitely just define a canonical form? I don't think it's. I'm not worried about the claim. I'm worried about the proof of the claim, right? I mean, yeah. And with that, we can define the Lebesgue integral. So here it is. If phi is simple function with canonical form phi of x equal to the sum, ck chi fk. Then define the Lebesgue integral as the integral over Rd of, so by the way, I think maybe that the E is supposed to be taken to be all of Rd. Phi of x dx. Sum k equals 1 to m of ck, the measure, the measure of fk. Remember, we assumed that the sets E sub k were measurable. And so what is fk? It's nothing more than a union of the EKs, right? Okay. So that's the definition of the Lebesgue integral. Well, for simple functions, right? And so then he points out the properties of this Lebesgue integral. Although he says that he also defines the integral over E of phi of x dx to be the integral over phi of x chi E of x dx. To emphasize the choice of Lebesgue measure, you sometimes also see this written as the integral of phi of x dm of x over Rd. He says, or sometimes you just write integral phi. Sometimes integral phi is that. Don't tell the Calc 1 students, right? Yeah. They always leave off the dx. Yeah, it's true. So what are the properties? Independence of representation. In fact, while we've used the canonical form to define the integral, because that way we have a definite, a precise definition that's unambiguous. If you took any other representation for phi, like we started with, and then almost undid carefully, as was criticized by you guys, right? If you go back to this original, our original, possibly overlapping whatever decomposition of the simple function, it would give you the same. Like this, in my current notation, would also be equal to the sum k equals 1 to n of a sub k measure of E sub k. I should use a different index here. It's just bothering me to not use a different index for these different. It's just a point of personal style. But independence of representation is one thing. Also, we have linearity. The integral of the sum of simple functions. If we have phi plus gamma, then we have integral phi plus integral of gamma. You can pull constants out. all right? This one is important to me. This is really part of the reason I'm interested in this whole discussion. If we have the integral over the union of E and F of phi, and again, phi is a simple, this is all for phi, a simple function, all right? And phi being a simple function, it's really quite simple. I mean, they're dumb. If we're in d equals to 1, what's the graph of a simple function look like? Bunch of what? Bunch of what? It's just a step function with, it's just like skyscrapers, you know? Not interesting ones either. So this is the sum of this and that. For what? That assumes something about E and F. Yeah, disjoint. So if E and F are disjoint, then the integral of the union is the sum of the integrals. If you have that phi is less than or equal to psi, then the integral of phi is less than or equal to the integral of psi. All right. And likewise, you have that if we have the absolute value of the integral of phi, it's less than or equal to the integral of the absolute value of phi. So he calls this the triangle inequality because it's literally the triangle inequality here in the current context. But this litany of properties, independence of representation, linearity, additivity, monotonicity, and triangle inequality, these 4 properties of the Lebesgue integral are going to be repeated for us as we go through the chapter at each stage of sophistication. All right? These continue for every step in our building up of the real definition of Lebesgue integral. These stick with us. This, to me, right here, guys, is one of the reasons I think it's worth really looking at the Lebesgue integral. Let me show you why. I think that's probably a good place for us to stop in terms of development. We'll go on to the next step next time. I'm going to spend the next 10 minutes talking to you about the Riemann integral. How did you guys define the Riemann integral? You what? Did you say you didn't? Let me. So here's the naive Riemann, right? So I think different naive Riemann would be something, for me, it'd be something like this: integral from a to b, f of x dx, right? We assume, certainly, let's keep f of x continuous, right? I mean, of course, you can extend Riemann to be. I mean, you don't have. I mean, we can go more than just continuous, right? I mean, Riemann still makes sense for discontinuous as long as there's a finite number of discontinuities, right? But the definition that I usually see is something like this: the limit as n goes to infinity of the sum I equals 1 to n of f of x sub I star delta x, where we set up a partition, right? A equals to x sub 0, which is less than x1, which is, which is less than x2, which is less than xn, which we'll call b, right? And I usually set up the partition, and this is why I say naive, because I'm assuming that x sub I minus x sub j, x sub I minus x sub I minus 1 is equal to delta x for all